So let's take a few more examples regarding the finite state machines. And this example is about a sequence generator. Now you should carefully look at the problem here. And it reads that we have to design a circuit that has 4 outputs. So it's explicitly mentioning that your circuit should have 4 external outputs. Fine. And the circuit should be such that it should generate the sequence of output patterns. I mean, the sequence given here, where the first one is 0001, 0011, then 1100, 1000. These numbers should be displayed at these outputs. For example, for the first case, 0001, it means W should be 0, X should be 0, Y should be 0, and Z should be 1. So we have to design it in such a way. And after the last sequence is generated at the output, the circuit should repeat the sequence. Fine. Now this is a slightly different problem because in this explicitly it's mentioned that this pattern should be displayed at the output. Fine. So again, the methodology we have here in the first step is we have to capture the finite state machine. So this is our first step of the methodology, that we have to capture the finite state machine. Now here I have 4 patterns, which means that this machine will have 4 states. But you have to be very careful that these states, these patterns are not the output of the states. You can't use these patterns to name your states, right? Because then they will be state outputs. Whereas in the problem, it is explicitly mentioned that these are external outputs. These outputs have to be displayed, fine? So it is something like this. Let's call this this state, let's say state A, and then let's call this B, C, and D. Now in the state A, my output should be 0001, means W, X, Y, Z. Fine. Then when I move to state B, my output should be 0011, means in this state, my external output W should be 0, X should be 0, Y should be 1, Z should be 1. Similarly, in state C, 1100. Then in state D, 1000. Fine. So it should be something like this. Fine. Then let's assume this is my initial state, and every time a clock happens, I will move from one state to the next state. Then I'll come back to my initial state. So this will be the finite state machine. Second is we will have to capture the, sorry, not capture, we will have to create the standard architecture. Fine. Now here I have 4 states, and 4 states you can explicitly represent using 2 bits. So I will need a 2-bit state register to start with, because in this what you call standard architecture, this is something we have to explicitly specify. Okay, what is the width of my state registers? Fine. So this is my 2-bit state register. As you know, it will have a mandatory clock. So this is a 2-bit state register. So from this state register, before that we also have to show the combinational logic. So let's say this is my combinational logic, which we will resolve in the coming steps. Fine. Now from the 2-bit state register, I will have 2 state outputs. S1, let's use this arrow, S1, S0. Fine. Also, we will have from the combinational logic 2 next states. So it will be something like this. n0, n1. So let's name it. So this will be s1, s0, then this right here will be n0, then this will be n1. And then finally, I will have 4 external outputs: W, X, Y, Z. So this will be the standard architecture. Fine. But please be careful. The question itself, it demands that these patterns, they should be displayed at the external output. If the question says that you have to design a circuit that just counts through this sequence, then okay, we don't need external outputs. We can actually encode the states using that count. But here it explicitly mentions that your circuit should have 4 external outputs, W, X, Y, Z, and it is at these outputs where your pattern should be displayed. Fine. So this is the standard architecture. Third step is we have to encode the states. Third step is we have to encode the states, wherein we have to assign a unique code to each of the states. So in this case, it is pretty straightforward. We have 4 states. We can use 2-bit binary numbers. So it will be like this. As far as the output goes, external output, it is something like this. Then this is my initial state, and these are the transitions. Now, initially, I named the first state A. Now I will assign a code. Let's say 0, 0. Similarly, sorry. So this is the encoding of the states. Then we'll have to create the state table. Wherein we list the inputs and the outputs. Now, as far as inputs are concerned, we only have state inputs, S1, S0. But outputs, apart from the state outputs, we also have the external outputs, W, X, Y, Z. These are my external outputs. And then my state outputs, which define the next state as N1, N0. Fine. Now with 2 inputs, you can only have 2 combinations, 0, 0, 4 combinations. And for every combination, I have to actually determine what my next state is and what is the output for that particular state. So when I am in 0, 0, my output should be 0, 0, 0, 1. And from 0, 0, my next state will be 0, 1. When I am in 0, 1, my output should be 0, 0, 1, 1. Next state 1, 0. When I'm in 1, 0, output should be 1, 1, 0, 0. Next state from here on will be 1, 1. And when I'm 1, 1, output should be 1, 0, 0. And from here I will be moving to the state 0, 0. Then fifth step is we have to implement the combinational logic. You can get the equations here. For W, it will be these two, S1, S naught complement plus S1, S naught. Fine. You can actually solve it using Boolean laws. Take S1 common, S naught complement plus S naught. So it will be simply S1. Similarly, X would be, it has only one term, S1, S naught complement. Y will be S1 complement S naught. Then Z has 2 terms, S1 complement S naught complement plus S1 complement S naught. Again, if you solve it, it will be S1 complement. And then N1, you can see it is S1 complement S naught plus S1 S naught complement, which basically is S1 XOR S naught. And N0 is S1 complement S naught complement plus S1 S naught complement. Again, if you take some terms common, it will simplify to S0 complement. These are the 6 equations that I will implement, and that will actually resolve my combinational logic. So my overall circuit will be something like this. I will have the state resistor, which I specified earlier. So I will have a state resistor that we have already specified. It's a 2-bit state resistor. And from here, I will have 2 inputs. So this is a 2-bit state resistor. This will give me my 2 inputs. Say one input S1 and the other one S0. Fine. So this one is S1. This right here is S0. Now W is simply S1. So we don't have to do anything. Fine. So W will be directly the output S1. So, okay, first of all, I always forget this. It will have a mandatory clock. Okay, let's start implementing. Starting with W. So W is directly S1. So if I tape out from here, this will directly be my W. X is S1 complement. So this is S1 complement ANDed with S0 complement. So this is my X. Fine. Then Y is okay, X is S1 S0 complement. So okay, we have to, let me just redo this. S1 is directly this, and S0 I have to pass through a NOT gate. So this is X. Fine. Y is this. Okay, this I have this. Y is, so this is S1 complement S0. So we don't have this. Fine. So I have complement here, direct input from here. This will be Y. Then Z is directly S1 complement. So this will be Z. And then the next outputs, N1 is S1 XORed with S0. So this is N1. Fine. And N0 is S0 complement. So this is S0, S0 complement, and like this. Fine. So this will be the circuit that will actually output these. But you have to be very careful. For example, if I modify this question, I have already written it. I have modified this question wherein I have to design a sequential circuit that counts through the sequence this, which the sequence is same. The only difference is that in this circuit, you will have to actually count through the sequence. Wherein the question that we just solved, we had to actually display this pattern, this sequence at the output. So if you try to solve this, the state machine will be something like this. It will again have 4 states because you have to count through 4 states. But this time round, the pattern itself will be the encoded state. So something like this. So there will be no external outputs. There will be only state inputs and state outputs. And there will be 4 of them. Huh? So this will be the initial state. And these will be the transitions. And so when you create the standard architecture, although again there are 4 states, this problem also rose in when we designed that ring counter. But the thing is that it is explicitly mentioned that these 4 states need to have this count. Fine. So you will have, when you go for a standard architecture, it will have a 4-bit state register that will generate 4 state inputs S3, S2, S1, S0, and 4 next state outputs N3, N2, N1, N0. And the rest of the steps will follow. You will have to, after creating the standard architecture, it is already encoded, then you will have to create a state table wherein you will have to exploit those don't care conditions if they appear. Fine, because in this case, with 4 bits, you can have 16 combinations and only 4 are valid. So you can have that, and then you can come up with the circuit that goes. So the main point here is to differentiate between the way the problem has been put forth. If it is put forth explicitly mentioning that these patterns or these sequence have to be displayed at the output, you will have to consider the external output. If it is mentioned that the circuit should actually count through this pattern, through these sequences, then you can use these sequences to encode your states, right? And you will have different circuit implementations, right? So I'll stop here.